His right hand's stronger.
I'm Steve Snyder, representing for the purple team. We're at the filter wash station. And this week we're talking about the root locus. That's the emphasis of this week's presentation. So the rest of my team is Roger, Randy, and Ross. This week we'll talk about the filter wash station background, steady state operating curve, step response, the transfer function, or the MOV003 model, sign response to the relay, which are both response models, the root locus, and the focus this week is the proportional controller, and I'll finish up conclusions after that. Here's a schematic of our system. It's a centrifugal pump. It's control. Here's the block diagram, steady state operating curve. Here's the steady state operating curve. This has an average slope of about 0.13. It's vaguely linear, but not quite.
So easy. Best presentation ever.
Because we were fixing everything last week, right?
Lack of ding. I don't know.
You can go back if you want to.
No, that's cool. This is the Bodie plots. Here are the results for the Bodie plots, and there are questions. Most of them were pretty well on there. We had a little bit of miscommunication, so we did region A. We had 25 to 100%, and then 75 to 100%. So we had a slightly interesting overlap there. You can see the only variation really was in tau, where we had the full region. We had a tau of 0.6, which really closely relates to the rest of our data, and then we came up with a tau of 0.13, which is not at all close, and we're not sure what happened there. We're looking into it. Relay feedback is another response setup. Here's an example of what the relay feedback looks like. It has a floor and a ceiling value. Floor, ceiling. These are the ways that tau, K, and T naught were found for the relay experiment. T is the period. Delta C and V were also used in that. Delta C over delta M was the amplitude ratio, and the average was 0.27. The period average was 2.2, and B average was 0.43. Here are the equations that were used in order to find the model values for the relay system, the relay feedback model, sorry. Here's a chart showing the comparison of the K's used so far, with an emphasis on the Bodie and the relay. You can see that the Bodie comes in significantly lower than the rest of the K's found in the lower region, and is a little bit higher in the mid-range, is a high mid, and a valley pool in the very high range. The rest of the systems in comparison there are the step-up and the step-down model, skipped over previously. The step-up and step-down experimental values, and the model SSOC slope. It's the same thing for T naught. You can see that the relay and loading values for T naught came in a little bit higher than previously found for the rest of our experiments. And a comparison for tau. These were kind of all over the place. They didn't really have a very specific trend in anything coming in higher or lower. Here's the root locus plot that was used as a model to find KC values for specific decay ratios. For a decay ratio of 1/500, 1/500 was decay of 1, 1/10 was a decay of 13. That was backwards. KC, right, sorry. Decay ratio of 1/4 was a KC of 18, and then our ultimate KC was 27, and our critical decay was 0.4. also our ultimate frequency was 0.7, and our ultimate omega was 4.2. Here again are those same values. This is what was predicted by the root locus plot. We had a critical decay of 0.4. 1/500 was 4.7. Root locus said that 1/10 was 13.3, and that 1/4 decay was 18, and ultimate decay was 27.2. These are values that were the exact same for 75 to 100 because it's all used the same tau for the whole system. Here's an example. This is these are a little out of order, and I apologize for that. This is an example of the proportional response. This is for the 1/10, which is skipping ahead a little bit, but it just has a good curve, so it shows well what's going on here. In order to find the amplitude ratio, it's C over V, which is where the 1/10, 1/4, 1/500 comes in. The step value change is delta R. In my case, this was for 75 to 100%, so I didn't have room to step up, so I did a negative step down of -2. The offset, this is what the customer wants. This is coming in at 17 pounds per minute with a -2 step. They want 15 pounds per minute. The offset is the difference between what the system is giving them and what the customer wants. Here's an example of our critical decay of 0.4 and a decay ratio of 0. As you can see, it's completely monotonic. There's no oscillation in this. There's a really high offset. You can see that this is after 20 seconds, it's still almost steady with the set point of 17. There's basically no movement showing that it's in critical decay. Here's 1/500. You can see this beginning to oscillate. It's not much at all. It still has fairly high offset. Here's critical decay of 15, which is equal to 1/4 decay. You can see that we've gotten into some overshoot here where the system overcorrected in order to try and meet its new goal, and then it began to bounce fairly excessively before it levels out towards 20 to 30 seconds at a closer offset, certainly than the critical decay values were. And here's the ultimate decay, ultimate KC, I'm sorry, with a decay of 1 for the 75 to 100% range. You see there's a lot of overshoot. It's completely oscillatory. It never settles down. It's just a completely unstable response from the motion controller. Here's a plot showing the differences between what the root locus predicted in its model and what we found experimentally in our system. Blue is the root locus here. This is for each individual decay ratio, and then here are the predicted and found KC values. You can see that let me show you. The root locus values were exceedingly higher across the board than the KC found experimentally. Also, the offset trended with decay ratio as well. The offset got smaller as the decay ratio got higher. So just to show you that there is compromise involved in choosing this, it's not a simple larger KC value or larger decay ratio value. You win some and lose some. In conclusion, the FOPDT models for this system's step response were very close to experimental results. Our K came out at 0.1, T naught was 0.7, and tau was 0.6. In most cases, the coefficients found graphically were similar to those in the models and the Bodie plots. The values of KC were similar in the Bodie chart, the relay, and the root locus model. The root locus plot produced consistently higher values than the system shows. And to try and shoot for that compromise, a KC value near 8 with a decay ratio of about 1/10 would be recommended for the flow system operators. To show you a picture of what I'm talking about here, this gives some oscillation in its response, and it gives a minimum offset with that oscillation. You get either a lot of oscillation and good offset, and you get no oscillation and terrible offset. So this is a pretty good pretty good compromise between those two. So this is what we would, as a flow system team, suggest to the flow system operators that would be a good choice for their system. Does anybody have any questions?